Hello everyone, we are from Koc-University Mechanical Engineering Department and this is our senior design project DUM-E. It's a tracked vehicle with an object manipulator. I'm Yağmur, my friends are Alp and Şeyhmus. We had such a problem that there's a need for different way to collect samples from hazardous environments rather than only relying on humans to do it. The objectives were developing a tracked vehicle with a robotic arm from hazardous environments, and we would integrate sensors and control systems for data collection and autonomous decision making. We would design the robotic arm to accurately collect contamination samples up to 250 grams. Then we would test and evaluate the systems for reliability and durability. Here are the computer-aided designs of the components of the robot. We have a robotic arm of 3 degrees of freedom. We have the main body, we have a gripper, and we have the track system. And this is the assembled view of the computer-aided design. And this is our vehicle dummy.
Here is a demonstration for the mobility of the dummy. It takes commands from the desktop application to execute its movements. Here is the gripping in action. Our microcontroller controls lots of different motors and sensors or reads data from them, including ultrasonic distance sensor, force sensing sensor, wireless communication sensor, DC motors and servo motors. Here is the embedded software sequence diagram. With desktop application and one wireless communication module connected to the USB to UART converter, it is achieved to send data to the other wireless communication module attached to the Arduino. For the static structural analysis, we decided to conduct a simulation on critical components, such as the driving pulley and lower body of the robotic arm, and examine the worst-case scenarios during the simulation. For the driving pulley, we simulated the condition where the DC motor applies full moment to the shaft of the driving pulley, however it cannot rotate it, which will result in a maximum shear stress. For the lower body of the robotic arm, we simulated the condition where the moment effect of the weight of the components will be maximum, since this state results in the highest von Mises stresses on the lower body of the robotic arm. For reducing the number of boundary conditions resulting from the contact of the bodies, we transformed all the forces resulting from the upper bodies and their moment effects to a reference point, and conducted analysis in this manner. Here are the results.
For the top part of the vehicle, we ran a simulation to investigate its durability under 5 kg load. Here are the results of the simulation. This is the MATLAB simulation for the robotic arm. We had assumptions such that 2 elliptical paths were defined for the motion of the gripper. The coordinates of the path were defined as x and y. The code asks for position of object as x object and y object as inputs. Alpha has a predetermined motion between angles pi over 4 to 3 pi over 4. Tolerance for the solver is adjusted as 10 to the power of minus 4. Newton's method is used to solve the set of equations which results in angles of motion. The methodology includes system of equations as below, and they were solved by Newton's iteration method. Here are the results of the simulation of the robotic arm. The code gives us the servo angles in 3 joints. We use these final and initial angles to create motions of the robotic arm. Here you can see the feature plans of our project. We will expand the capabilities for larger or heavier sample collection. We can add sensors and instruments for improved data collection and developed remote control. Also, we may explore commercial or industrial application. We can integrate the system with drone or aerial vehicle for hard-to-access locations. And lastly, we may conduct tests to optimize the durability and efficiency of the system. And special thanks to these people that helped us during our project.